Hello and welcome to lesson 3 in this series on application generation. Today we're going to be looking at translators. That includes interpreters, compilers, and assemblers. People and computers unfortunately do not speak the same language. Processors only understand something that we call machine code, binary sequences representing instructions and data. Machine code instructions consist of two parts: an opcode that tells the CPU what operation is to be done, and an operand which tells the CPU what data to use with the operation. The operand itself could be data, but it's usually just the memory address to find or send the data to. Back in the beginning, when we first developed computers, there was no choice but to try and write programs in machine code. This is a laborious task and would be prone to errors. Different processors had different instruction sets. The binary sequence to add two numbers for one processor could be very different from that of another. Or even the instructions available in one processor would not be available in another. This meant that a program would need completely rewriting to be moved to a different computer system. Due to these reasons, from the 1950s onwards, people started to develop languages that would be easier for humans to program with. However, all the code produced by these languages needs to be converted into machine code before it can be executed by a CPU. Remember, the CPU only understands machine codes, ones and zeros. The software that does this is called a translator. And there's three types of translator we need to know about: assemblers, compilers, and interpreters. Let's start by looking at what an assembler does first. So by using mnemonics to represent the opcodes, code became somewhat easier to read and write. We call this new language assembly code. So if you look here, we can see we've got a machine code instruction, and that's quite difficult to remember, it's quite difficult to create, whereas this is a lot easier to remember. In fact, remembering this whole program and being able to write it is much easier than trying to remember the equivalent in machine code instructions. So an assembler is a program that converts assembly language into machine code. There's usually a one-to-one relationship between assembly and machine code. So each opcode mnemonic and operand in assembly code will translate directly into an opcode and operand in machine code. This means that on the simplest level, an assembler just needs to translate each line of code into its binary equivalent. However, as with machine code, assembly code isn't very portable. Assembly code for one processor is extremely unlikely to work on another. So again, you'd have to rewrite a program to move it from one CPU architecture to another. So by the late 1950s, the limitations of writing assembly code were becoming clear. Even with the significantly higher relative cost of hardware back then compared to now, companies were still finding they were spending much more on the development of software than purchasing new hardware. The solution to this was the first high-level language called Fortran. So a high-level language is one that consists of more human-readable statements. People quickly saw the benefits of coding in high-level languages and started writing programs in this way. For an example of this, let's take a look over here at some x86 assembly code. Simple program, it just prints hello world on screen, but you can see here the assembly code is quite complicated. Whereas we look at a high-level language, this is Fortran, but you could do this in Python or C# or whatever language you wanted to. A hello world program is essentially one line of code. So we can see that the high-level code is much easier and simpler to program in and understand than assembly code. Over time, many high-level languages have been created. Basic C, C++, JavaScript, Python, Java, there's a whole bunch of them. While high-level languages are much easier for humans to understand, we still need a way of converting them into a form that the CPU can use. So to convert from high-level languages to machine code, we use two types of translator program. We can use an interpreter or a compiler. Starting first with interpreters. An interpreter takes each line of high-level language program, converts it into machine code, and runs it. This is useful for debugging a program, as the program can start running straight away and will stop at a line if it finds an error. The downside of this is that an interpreted program runs slowly. Every time the program is run, The user has to wait for the translation of each line as well as the execution. So when iterating through a loop, the interpreter may have to translate the same line many times. To run the code, the user needs access to an interpreter, which itself will take up some of the system's resources, as in CPU clock cycles, memory, RAM, and storage. There's a huge selection of interpreted languages: Python, JavaScript, PHP, Ruby. There's lots of interpreted languages out there that we can use. Moving on to compilers. A compiler is a program that takes a program written in a high-level language and converts it into machine code. It does this all in one go. This can then be distributed to anyone with a compatible system without the need for any additional programs. Once the code is compiled, it can be run as often as needed and at a much faster speed than an interpreted program. Also, if the source code were distributed commercially, people could amend this, removing anti-piracy measures, rebrand the product and sell it on, or copy any innovative ideas into their own product, thus stealing a company's hard work. As the compiled machine code is not human readable, doing any of these things is much harder. Small programs such as the one we often write on an A-level course will compile in a matter of seconds. More complex programs, however, might take minutes or even hours to compile. Some common compiled languages including C, C++, C Sharp, Fortran, Pascal. Again, there's a lot of them out there. Also, please note some languages can be interpreted or compiled depending on what you want to do. So here is a comparison of compilers and interpreters. Interpreters spot an error in the source code right away because the command is carried out immediately. Compiler errors are picked up during the compilation process, but this often leads to more hard to spot errors. Interpreters are less prone to computer crashing. Some interpreters execute code within a virtual machine, which insulates the host computer from defective code. We'll take a look at a couple of examples of that later on. With a compiler, the executable file runs directly on the computer, and so poor code can crash it. Interpreters are slower to run compared with compiled code, as every line has to be translated on the fly every time the program is run, whereas the compiler is faster, as all the translation of machine code is done in one pass when you first compile the program, and then the compiled machine code is stored as an executable file. With an interpreter, well, source code is sometimes considered intellectual property, and owners want to keep that private. But interpreted code is easier to reverse engineer back into source code and reveal how it works, whereas with compiled code, you have that executable file, and that's difficult to kind of go back, reverse engineer it, and work out the source code. Question I often get asked by students is, how were the first compilers written? Well, a compiler is a programmer, a compiler is a program. It needs to be written and generated like any other. The first compilers would have been written in assembly code and then created using an assembler. These first assemblers, if we take another step back, would have been written originally directly in machine code. Nowadays, a compiler can be written in any high-level language and then compiled using that language's compiler. Once a compiler exists for a language, it is now normal practice to write a new version of the compiler in that language itself. Hope that's clear. And just have a little note here about virtual machines. I mentioned that a couple of slides ago. Another type of translator is one that translates source code into an intermediate set of instructions that we call bytecode. This bytecode itself is then run on what we call a virtual machine, a kind of pretend machine implemented purely in software. Java is the most famous example of this. So if you have a look at this little diagram at the bottom here, so you can see here we've got the Java source code, we compile it into bytecode. This is an intermediate stage. This bytecode can then be put onto any machine, any type of platform that has a Java virtual machine written for it. And this Java virtual machine can interpret the code and then run it on whatever type of operating system it's running on. And this is why Java became very, very popular back in the 1990s, because you could create the code once, and then it would just run on any platform. You didn't have to compile it for each individual platform. You compiled it once into the bytecode, and then that could run on any computer that had a Java virtual machine written for it. Everything from a PC to, I don't know, smart television or something like that. Anything in between. And to finish off, just a little bit of a language note about something called object code. So if you read about this subject you'll often see the term object code being used interchangeably with the term machine code. And sometimes I get students asking me about this, so I'm just going to look at this in a little bit more detail. Technically, object code is an intermediary step sometimes taken before a fully executable program is produced. Object code is a portion of machine code that has not yet been linked into a complete program. So what happens when we compile our program, we might end up with lots of different object files, plus possibly library code that we've imported into our code that needs to be linked together into a final executable program. The object code contains placeholders where library code needs to go. Once a linker has been used, machine code that can be run directly on that processor is produced. What is the linker? That's just simply part of the operating system who has the job of doing this, and we'll look a little bit at linkers in a future lesson. In summary, although people program in a variety of languages for different reasons, computers can only understand what we call machine code. So we need a variety of translator programs to convert between more human-readable languages and ones and zeros. The three types of translator program you need to know about are assemblers, interpreters, and compilers. That'll be everything from me today. I hope you found this lesson useful, and I'll see you in a future lesson. Have a good day.